Assalamualaikum and hi everyone. Today we are from group 2 and we are going to present for our group project Mechanic of Materials. So our group have been made up of 5 group members, which is Muhammad Hassan Syairazi, Danial Asyaqirien, Ruth Ronnie, Muhammad Nabil Aiman, and the last one is Wong. Moving on, for the introduction, for project background, the first one is Mechanic of Material, where we focus on analyze how different solid structures respond, deform, and withstand various types of applied external loads. The second one is bending behavior. We focus on structural members subjected to lateral loads, which induces internal normal stresses, shear stresses, and physical deformation. The third one is we use spaghetti as a model, where we utilize a circle bar of uncooked spaghetti as an experimental prototype. And the last one is destructive things, subjects the fabricated model to be controlled, progressive weight load, monitoring its behavior continuously until it reaches its ultimate breaking point. Next, this is our project specification, where we need to build a bar with the bar length of 30 cm and its diameter 1.5 cm. Moving on, we go to the apparatus or material that we use to build our model. The first one is uncooked spaghetti. The second one is hot glue gun. We use hot glue gun to stick the spaghetti together. Epoxy resin glue, cloth tape, and the last one is sandpaper.
Now I will explain the fabrication procedure of our spaghetti bar. First, we align all the spaghetti strand to a length of 30 cm. Then the strand will then bundle together to form a solid circular bar with a diameter of 1.5 cm. Next, we apply epoxy adhesive to bond the spaghetti strand together. The epoxy helps increase the strength of the bar by reducing the movement between the strands. And after that, we wrap the tape around several sections of the bar to keep the strand together and maintain the circular shape during testing. And finally, we check that the bar had a uniform diameter and the required length before carrying out the loading test. Next, for the loading procedure, first the spaghetti bar was placed horizontally on two supports. Then a 1.5 liter water bottle was placed at the center of the bar. So additional 1.5 liter water bottle were added one by one until the spaghetti bar broke. And finally, we record the total load that caused the failure and observe the location where the bar fractured.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hassan Syairazi Zakaria.
My name is Asyaqirien and Zawawai.
My name is Muhammad Nabil.
My name is Wong.
My name is Abdul.
So today we are going to do our model testing. So we are from group 2. We will be testing our beam with a circular area. The area is 1.5 cm diameter with 30 cm length. Let's go.
So our beam can hold up to 4 bottles.
Okay.
Now, let's move on to the result. So for each load, we have 1.5 bottle of water, and then we add the load until the breaking point, which is 4 bottles, which adds up to mass of 6 kg and also weight 58.89 Newton. So for the first bottle's calculation, we have our mass, which is 1.5 kilogram, and then we can calculate the weight, which is 14.715 Newton. Now let's draw the free body diagram. We have our weight in the middle, and then we have our force of AY and also BY. The weight is 15 centimeter from the left side of the beam. So we can calculate the force of By by using summation moment equals to 0, we got 7.3575 Newton. And then we can calculate the force Y. We can calculate the force Ay using the formula summation Fy equals to 0. We got 7.3575 Newton. Let's move on to the second loop. I'm sorry. Now we are splitting into segments. Now for the segment 1, we can put the V1 pointing downwards and also the moment. So to calculate the V1, we can use summation Fy equals to 0. And then to calculate the moment 1, we can also use summation moment equals to 0. Then for the second segment, we can use also summation Fy equals to 0, and we got the V1 and also the same formula summation moment equals to 0 to get M1, which is 0. So for the graph, this is the V. For the V graph, we got the shape like this, and then for the moment graph, we have a peak in the middle. So for the second load, which is 3 kilograms, we have our mass is 3 kilogram and our weight is 29.43 Newton. So for the free body diagram, it's the same. Just change the weight to 29.43 Newton. We can use the summation moment equals to 0 to get the By, and we can use summation force equals Fy equals to 0 to get the Ay. Then we split into two segments. For the first segment, we need to find the V1 using summation Fy equals to 0, and we got 14.715 Newton. And then we want to calculate M1 using summation moment equals to 0, and we got 2.2073 Newton meter. For the second segment, we will do the same, which is summation Fy equals to 0, and then we got V2 equals to negative 14.715, and then moment 2, we got 0 by using the summation moment equals to 0 formula. And then this is the graph, same shape but different values.
So for this slide, we have our volume, which is 4,500 ml, where the mass is 4.5 kg and the weight is 44.145 newtons. Then we can construct our free body diagrams, where there will be force Ay at point A and then force By at point P. The weight will be located at the center of the beam, which is 15 cm from point A. We can use the formula summation of moment A equals to 0 to get By, which is equals to 22.0725 newtons. And then we use the formula summation of Fy equals to 0 to find Ay, which is 22.0725 newtons. After calculating for the external forces, we will now look at the internal forces. For these cases, we use the method of sections, where it will be divided into two segments. For the first segments, we have our force Ay, which is 22.0725 newtons, and our V1 and M1. For V1, we will get a value of 22.0725 newtons, and M1 is 3.3109 Newton meter. For the second segment, it will be until 30 cm, where there will be force Ay, our weight at the middle, and then V2 and M2. For V2, we will get a value of negative 22.0725 newtons, and M2 will be 0. And then from there, we can construct two diagrams, which is first is the shearing force diagram, and the second is the moment diagram. For the first diagram, at the left side of these slides, we can see that V1 is 22.0725 newtons, and V2 will be negative 22.0725 newtons. For the moment, we can see that the maximum moment will be 3.3109 Newton meter. And we will get a moment equals to 0 at 0.3 meter. For this part, we have our volume, which is 6,000 ml, where the mass is 6 kg and our weight will be 58.86 Newton. We will then construct our free body diagrams, where there will be force Ay at point A, force By at point P, and our weight will be located at the center, which is 15 cm from point A. We will then use the formula summation of moment A equals to 0 to get the By, which is 29.43 Newton. And then we use the formula summation of Fy equals to 0 to get our Ay, which is 29.43 Newton. we can divide our beam into two segments. For the first segment, there will be force AY, which is 29.43 Newton, V1 and M1. The length will be 15 cm. We will use the formula summation of Fy equals to 0 to find V1, which is 29.43 Newton, and our M1 will be 4.4145 Newton meter. For the second segment, there will be force AY, which is 29.43 Newton, the weight 58.86 Newton, V2 and M2. We also use the formula summation of Fy equals to 0 to get V2, which we will get negative 29.43 Newton, and the summation of M equals to 0, where M2 will be 0. From the shearing diagram, we can see that the V1 is equals to 29.43 Newton, and our V2 will be negative 29.43 Newton. For the moment diagram, it will be going up, and then the maximum moment will be 4.4145 Newton meter, and M2 will be 0, which is located at 0.3 meter. So for this part, we need to find the allowable normal stress. For the first steps, we need to find the moment of inertia, where we use the formula I equals to 1 over 4 times pi times r to the power of 4. The radius will be 0.0075 meter. And then we will get our moment of inertia is equals to 2.4850 times 10 to the power of negative 9 meter to the power of 4. And then from there, we can calculate our maximum normal stress, where the M is the maximum moment, which is 4.4145 Newton meter, and then C is the radius, 0.0075 meter. Our I is the moment of inertia that we calculated just now, which is 2.4850 times 10 to the power of negative 9. And then we will get our maximum normal stress, which is 13.4698 megapascal. And then it was given that the safety factor is 1.5. From there, we can use the formula allowable normal stress is equals to maximum normal stress over safety factor, where we will get our allowable normal stress, which is 8.9799 megapascal.
Alright, moving on to the conclusion of this project. This project successfully demonstrated the bending behavior and failure characteristic of a spaghetti beam subjected to a gradually increasing central load. A spaghetti bar with a length of 30 centimeters and a diameter of 1.5 centimeters was fabricated using epoxy adhesive and tape before being tested under progressive loading. The beam was able to withstand loads of 1.5 kg, 3.0 kg, and 4.5 kg, but ultimately failed when applied load reached 6.0 kg, which is approximately 58.86 Newton. From the experiment calculation, it was observed that increasing the applied load increased the bending stress and deformation of the beam. The beam eventually failed when the applied stress exceeds its length. This behavior agrees with the theory of mechanics of material, which states that simply supported beam experience the highest bending moment and stress at its midpoint under a concentrated load. Some factors may have affected the accuracy of the result, such as uneven alignment of spaghetti strands, differences in the amount of epoxy used, and small errors during fabrication. These factors could have influenced the strength of the beam and caused a slight difference between the theoretical calculation and the experimental result. Overall, this project provided a better understanding of beam bending, stress distribution, and structural failure. It also showed the importance of proper fabrication and natural properties in determining the strength of a structure. Therefore, the objective of this project was successfully achieved, and the experiment helped reinforce the theoretical concept learned in the mechanics of material course.